Hello, welcome to another session on statistics. So I hope you are liking the statistics series. If you have not watched the previous videos, please go back and watch the previous videos once. Because today's lecture, today's session is a continuation of the previous lectures. So I strongly recommend you to watch these recordings, these sessions in sequence, as all of them are connected with each other. So today we are going to start with a small, I would say, description, a small table which we will try to build, where we will try to show what kind of tests to be applied when. So there are a lot of hypothesis tests. So we'll look at what kind of tests to be applied when, and then we'll also look at few of the tests. So let's start writing hypothesis test here. What we already know is that hypothesis test is where we test a hypothesis which we call as an alternate hypothesis, and we try to form a null hypothesis. Then we try to find out the probability of the null hypothesis, and if the probability of the null hypothesis is low, we reject the null hypothesis and we accept the alternate hypothesis. Second scenario is we may not have enough evidence to reject the null hypothesis. So let's look at the hypothesis tests which can be done. So first division is between continuous data and here we have categorical data. So when it comes to categorical data, we use a chi-square test, which we will see in one of our lectures, maybe in this lecture as well. And then we have continuous data. So within continuous data, we have normal distribution, continuous data which follows a normal distribution, and non-normal distribution. So there are certain tests which only works with normal distribution and certain tests which works with non-normal distribution. So let's look at these tests, and here within normal distribution we can further subdivide this test. Actually, let's do it in the next slide. So we'll continue with this thread. This thread will look at normal and non-normal. So let's start with normal distribution. So within normal distribution, if we want to test with mean or if you want to test with variance, that decides what kind of test we actually want to use. So if we are testing with mean, then we have some tests. If we are testing with variance, then we have some test. So the test with mean are z-test, which we have extensively done in our previous videos, t-test, which also we have extensively covered in our previous videos. So if you have not watched them, please go ahead and watch. Then we have ANOVA, which we will cover. When it comes to variance, we have something called an F test. We'll have a test called Burlett's chi-square. We are not going to cover this test, at least in these videos. They are not much used, because when we are dealing with normal distribution, mean generally suffices. Now when we deal with normal distribution, as I said, mean tests generally suffices. Now let's look at non-normal distribution, which is this side. So we have covered this, we have looked at this. Now non-normal distribution, if we look at it, so here we deal with not mean but median, right? And that's makes a lot of sense, because non-normal distribution, the data is going to be skewed left, skewed right. So mean may not be the right matrix to deal with. So we deal with median, and we also have some test with variance. So here, if we want to test for variance, we use something called a Levens test, which we are going to see. And the other scenario is if we want to test with median. So if you want to test with median, we have tests like sign test, then we have Wilcoxon, then we have Whitney. So Wilcoxon and Whitney we are certainly going to discuss. And there are a couple of other tests as well. So one is called Kruskal-Wallis. So it's called Kruskal-Wallis. We are not going to discuss this test, but just good to know. Then we have a test called Moods median. This is all for when we want to test with respect to median. And last but not the least, if we want to test with median, we can also do a Friedman test, or I would say Friedman test. So a quick recap. From hypothesis test, we can do it on continuous data, we can do it on categorical data. Within continuous data, we can have normal distribution, we can have non-normal distribution. For normal distribution, if you want to test with respect to mean, then we can do these three tests. If you want to test with variance, then we want to do these tests. For non-normal data, If you want to test with median, then we can do sign test, Wilcoxon, Whitney, Kruskal-Wallis, Moore's median, Friedman. For variance, we do Levens test. Now you may ask, okay, why so many tests for median? Because they are tested, these tests are useful under certain scenarios with some other conditions as well. It's not only mean or median. Like in this case, as you remember in the last session I had said, that there are certain scenarios where we can do Z-test, there are certain scenarios where we can do T-test, and there are certain scenarios where we can do ANOVA. However, all of them are related to mean. Okay, so though we are testing for mean, but still these tests work for different purposes. The purpose is very, very different. So having said that, let's start the series of tests which we are going to discuss. So a quick recap on Z-test and T-test. So Z-test is used when the number of samples are greater than 30, when the population distribution is normal. And how do I know whether the population distribution is normal? We'll use something called a Shapiro test, which we'll see. Number 3, when the population standard deviation and the population mean are known. And number 4, when the observations are independent of each other. So in order to do a Z-test, these 4 prerequisites must be met. What are the prerequisites for a T-test? Population should be normally distributed. For that we'll use Shapiro test, which we'll see now. The variances should be comparable. For that we use Levens test. And yes, you're right. It's the same Levens test which we are talking about. So we'll see what that means. And number of samples are less than 30. If these 3 scenarios are met, then we can do a T-test. We can also do a T-test in case population mean and standard deviation are known or can be derived. For Z-test, we cannot do a Z-test if the population standard deviation is not given. Right? Even if the number of samples are greater than 30, but if the population standard deviation is not known to us, you cannot do a Z-test. So now let's take our hands at a Shapiro test. So we are going to remove everything and we are going to do it from scratch. So let's start. So now we have Shapiro test. So here what we want to do is we want to find out whether the weight of apples in grams, what we are seeing, do they follow a normal distribution or not. As we have seen, normal distribution is a must-have prerequisite for both Z-test and T-test. So now we are going to check how to determine if a particular distribution is normal or not normal. So here we have taken weight of apple in grams. So here I have sorted them in ascending order. So first let's look at it in a crude way, which we have done it previously as well. Just a quick recap. So what we are first going to do is we are going to calculate the standard deviation, as you can see, for all these 55 samples. And then we are also going to calculate the mean. So we have a total observation of 55 and we have standard deviation and mean. Now, in order to adhere to normal distribution, between one standard deviation to the left of mean and one standard deviation to the right of mean, we should have 68.2% of the data. So out of 55 records, 68.2 is 37.5. So between 13.53 and 20.97, we should ideally have 37.5 records. In this case, this has to be a whole number. So let's say take 38. So 38 records should be between this range. In our case, we find that 13.51 is this to 20.97. If we go, it's up to this. And we find 35 records, which we see here. Now between two standard deviation to the left and right of mean, that's what we have done. Two standard deviation to the left of mean and two standard deviation to the right of mean. If that is the case, we expect 52.5747. And if I take an absolute value of this, oh, sorry, absolute value will not give me the whole number. I was trying to find the whole number. Absolute value will only remove the signs. So it doesn't matter. That's fine. So here 52.47, which approximates to 52. In our case, we have 54 records. So 9.81, this first record gets excluded. And then from 9.41 to 24.69, here in this case, it stops in 23.9. So we expected around 52 records, we got 54. And between three standard deviation, 6.09 to 28.41, we expected 55 records and we have got 55 records. Fair enough. Now, can I say that this distribution is normal? Here we can see that there is slight variation. But is it okay if I say that the distribution is normal or not normal? So for that, we are going to run a test called Shapiro test. So let's run this Shapiro test. So now what we are going to do is, we are going to copy these comma separated values and we are going to calculate the Shapiro test. So first let's look at the histogram. If I look at it, it looks more or less like a normal distribution only. More or less. So now let's decode this slowly and steadily. Here we have got the mean, we have got the standard deviation, we have got the variance, we have got the kurtosis, all are okay. Now let's understand these three particular statistics in detail. Okay. So now what we are going to do is, let's understand these things in a bit more detail. So let's come here. So first, since this is a hypothesis test, what we are going to do is, we are going to form the null hypothesis and alternate hypothesis. So as I have said before, null hypothesis indicates stability. So it says data is normally distributed. Alternate hypothesis is that the data is not normally distributed, which is a state of some change, right? So whenever we observe change, we test that hypothesis, we form an alternate hypothesis and we test that hypothesis. So here, my null hypothesis is that the data is normally distributed. My alternate hypothesis is that the data is not normally distributed. So for Shapiro test, we use something called a W statistic. and the formula is that we get a W calculated, which we calculate from the data, and we get a W critical, which is the standard value. So for other subsequent tests, we are going to do this calculation by hand. So all the subsequent tests will follow this same formula, calculated and critical, calculated and critical. Okay. So we want to calculate this by ourselves, and this critical value is as per the standard. In this case, the tool has done the calculated for us. So the tool has done the calculation for us, and the calculation is 0.97. So I'll copy this. Calculated Shapiro Wilk statistic W, that is 0.97. Here the tool has already calculated it for us. So this is 0.97. And then what is the critical value? The critical value is 0.95. Right? So the critical value is 0.95 and the calculated value is 0.97. Okay. So what is this critical? What does this critical value means? That if I have to get a p-value of 0.05, what should be this value? I repeat, if had my p-value been 0.05, what would have been this value? Now, according to this formula, here it says if wcal greater than wcrit, then we cannot reject H0. If wcal is less than wcrit, then we can reject H0 and accept H1. So in this case, my wcal is greater than wcrit. So we cannot reject H0. We do not have enough evidence against the null hypothesis. If we want to be 95% sure for our alternate hypothesis, we cannot do that, because the chances of the null hypothesis being true here is more than 5% for sure, because the p-value should have been the critical value for p-value is equal to 0.05 is 0.95. If the calculated value was less than this, then I would have said that the p-value will be less or equal to 0.05. If the calculated value was 0.05, 0.95, I would have said that the chances of the null hypothesis being true is 5% and this is 95%. This is my critical value for my p-value to be 5%. But in this case, it is certainly more. Ideally, it should have been less. But if that is not the case, then we do not have enough evidence to reject the H0. What is my H0? That the data is normally distributed. I cannot say that the data is not normally distributed, at least from here. Okay, I do not have enough evidence to say that the data is not normally distributed. So probably I'll tend to believe that the data is normally distributed. Right? Now what I want to understand is that what is this actual p-value? Here we calculated again 0.05 and we saw that the calculated value is 0.97. But if it is 0.97, right, then what is the p-value? That I do not know yet. I just know that this is greater than 0.05 for sure. But what is that exact value? That I do not know. So let's try to figure that out from this calculator. So from this calculator, it's the same thing actually. So if we just put this value once more and calculate this test, right? So here, from here we can try to test the p-value. Let's try to calculate the p-value. So in our case, the W is 0.97 and number of samples is 55. So the p-value is 0.18. That means there is at least 18% chances. So here the p-value is 0.18. So in this case, I will tend to believe that it is normally distributed. It is having 18% chance, which is not very high, but certainly I cannot say that the data is not normally distributed. That is for sure. I have enough evidence against this fact. This is 82%, right? But I have to be at least 95% sure. And I am 82%, which is way less than 95%, right? So there's a fair enough chance that the data is normally distributed. And we also saw that. We saw that it's not perfectly normal, but like there's a fair enough chance, right? So there's an 18% chance of this data being normally distributed, and there's 82% chance that this data is not normally distributed. But in order to pass as a judgment that the data is not normally distributed, this is definitely we cannot say that for sure. Okay, so we can take this assumption and we can say that probably I'll somewhat lean towards the null hypothesis, because this is way less than 95%. Okay, very less, right? So this certainly cannot be true. That is for sure. So that's how we test normality of a distribution. This is something which we have done before. Just a recap: if the distribution is not normal, you can use log transformation, feature scaling, Box-Cox transformation to turn a non-normal distribution into a normal distribution, though it does not work always. Feature scaling does not work always. In fact, in most of the scenarios, it will not work. So mainly, we use Box-Cox transformation to turn a non-normal distribution into a normal distribution. Feature scaling is something which we will take a look at it later, but this is a footnote which we need to understand. Okay, now we'll go to the next test called the Levens test. So it's a test of equal for equal variance. So between two distribution, if I want to check if the variance is comparable or not, that's where we use the Levens test. So here we have two groups, right? So group 1 and group 2. Now what we want to find, the variance which group 1 has. Does group 2 have got the same level of variance? Like for example, suppose for example in country A, okay, I calculate the variance between the people for education. Suppose for education, or actually not education, let's do income. Right? So if I take the variance between income in country A, so this is what I want to find out. And I want to take country B, their variance in income. Can I compare these two? Are these comparable? Which means, suppose for country A, rich is say at 10, suppose an index 10, and poor is at an index 2, which means my gap is 8. In country B, suppose rich is at 15 and poor is at say 6, which means that the gap is 9. And I can say these 9 and these 8, they are like very close. The variances are comparable. The variation within country A and the variation within country B are comparable. That's where we use Levens test. So let's look at this test. Here in group 1 we have got 9 samples. In group 2 we have got 8 samples. But that's perfectly fine. It doesn't need to be the same. I just want to understand the variance, that the variation which group 1 has and the variation which group 2 has, are they comparable? So step 1, I am going to calculate their mean. I am going to calculate their average. So as you can see, this is the average for group 1. And this is the average for group 2. So now what we are going to do is, we are going to calculate the variance. So how to calculate the variance? So group 1, so each individual observation of group 1 minus the group 1 mean, and we'll square it up. So for this case, I take this minus this and then I square it up. Then I take this minus this and I square it up. So these are the numbers which we have got for the first one, for the second one, and so on. So as you can see here from the formula, this minus this and square it up. This minus this and square it up. This minus this and square it up. Right? For each observation, I am subtracting the mean, I am squaring it up. Now I do it for all the records for group 1, and I similarly do all the records for group 2. So for group 1, I am done. For group 2, I am done. Very good. Now what we will calculate is the degrees of freedom for group 1 and group 2. So we have calculated that. This is n minus 1. And here this is also n minus 1. So we have calculated the degrees of freedom of group 1 and group 2. Now we are going to calculate the variance. So the variance is this sum divided by the degrees of freedom. Here we are working with some samples, so we take degrees of freedom. And in fact, in Levens test, you have to use degrees of freedom. And here we calculate variance, this sum, where we have calculated the sum by taking the difference between two data points, the individual data point and the mean, then squaring them up, then adding them up, and that gives me the variance when I divide it by the degrees of freedom. Now what we are going to do is, we are going to divide the bigger variance by the smaller variance. And if I do that, so this is 17.94 divided by 17.07, and this is 1.05. Just by the intuitive look of things, we think that they are related. They looks to be related. Right? The variances looks to be equal, because the closer the F statistics is to 1, the better it is. Right? The closer the F statistics is to 1, the better it is. That means the two groups are comparable. Now we are going to look at the F table. So we'll open the F table. So here is our F table, and now as I had told you that we have to look at into the degrees of freedom of the numerator and the denominator, right? That's why we were calculating it, because that's required. So in this case, degrees of freedom is of the numerator, which is the bigger variance, which is this one, is 8, and the smaller one is 7. So numerator is 8 because the bigger variance is the numerator, and in this case the bigger variance is this one, group 1. So it's 8 and group 2 is 7. So 8, 7. So this is 8 and this is 7. So 8 will be this one. And this is 7. And if I go right up, I will see 8 is the second right. Yes, second from the right. So what we have done is correct only. Now we are going to look at the critical value for a p-value of 0.05 for the null hypothesis. So if the null hypothesis had to be true, right? The critical value, what is the critical value for null hypothesis? When the null hypothesis does not need to be true, sorry. If the null hypothesis has to have a p-value of 0.5%, then the critical value is 3.73, not 0.5%, sorry again. It's 0.05 or 5%. So the critical value is 3.73. So let's take 3.73. That's my critical value. So here my critical value, which I found from the F table, is 3.73. And my calculated value is 1.405. So let me just remove all these things. We'll do it fresh. So my critical value is 3.73 and my calculated value is 1.05. Now what we are going to do is, we are going to look into this formula, and what we see is that the critical value is greater than the calculated value. If that is the case, then we cannot reject H0. What is my H0? So the variance of two groups are equal. And what is my H1? Variances of two groups are not equal. So in this case, I cannot accept this hypothesis, because for that to be true, my calculated value should have been greater than the critical value. If that was the case, then only I could have rejected it. But in this case, I do not have enough evidence to reject it, which is all good. But I still am curious to know what is the exact p-value for this 1.05. I want to know that. Right? I know that it is certainly much greater than 0.05, because that, if you see the difference, is certainly greater than 0.05, but what is the exact value? This one I am not able to, I cannot accept. This one I cannot reject. But I am still curious to know what is the probability of this statement being true. So let's do that. Let's pick up this test. This online Levens calculator, we'll pick it up and we'll try to see and derive the p-value. P-value belongs to the null hypothesis, as you already know. So here my degrees of freedom of one is 8 and the other is 7, we know it. And we are calculating against 0.05. and we saw that it's 3.73, which we have already seen before. Now what I'll do is I'll try to play with the probability value and see if I can get close to 1.05. What is that p-value which takes me close to 1.05? So if it is 1, it is 2.75. So I still need to reduce. I'm still quite far off, say 0.2. 1.93, which means the p-value will certainly be more than 20% or 0.2. So let's make it 0.3. 1.51, in our case it's 1.05. So we still need to do more, say 0.35. 1.35, no, I am at 1.05. As you can see, my calculated value is 1.05. I want to find out the exact critical value, sorry, the exact p-value. So let's keep going, say 0.4. 1.22, which means okay, we still need to go further, say 0.5. 1.01, so it has to be between 0.4 and 0.5. So in this case, this is 1.05 and this is 1.01, right? And which means I have now gone below that critical value. So now I have to go back, say 0.46 or 0.45. Let's start with that. 1.11, okay, let's go slightly higher. 0.48 is 1.05, which means here my p-value is 0.48. Okay, that means the chances of this statement being true is 48%, which is a good enough number. For me, for a null hypothesis, this is a good enough number. So we certainly cannot reject this. The chances of this statement being true is 52%, right? So the chances of the null hypothesis being true is 48%, which is a good enough chance because it's as simple as, tossing a coin. When we toss a coin, the chances of a head is 50% and the chances of tail is 50%. So in this case, what are the chances of the variance, that the variance of two groups being equal? As high as the chances of getting a tail when you toss a coin. So it's quite high, right? So we have looked at Levens test, we have looked at Shapiro test, and we have also understood what test to apply where. We have looked at the conditions, the prerequisites of Z test and T test. Now we will look at some other non-parametric tests, which are Wilcoxon test and Whitney test. So we'll now look at Wilcoxon and Whitney test. If you come here, it's a non-normal test. We test it when the distribution is non-normal and we want to test for medians. So we are going to look at these two tests now, Wilcoxon and Whitney. Okay, so let's start on Whitney and Wilcoxon test. So as I have mentioned before, these tests are non-parametric in nature and mainly they are using median as the evaluation parameter. So what is a non-parametric test? So a non-parametric test is a test where the test can be applied to any kind of distribution. So far we have looked at z-test and t-test, which can only be applied for normal distribution. So let's look at Whitney and Wilcoxon test and the difference between those tests. So we have completed up to Levens. So let's look at Wilcoxon test. So Wilcoxon test is used if the population distribution is not normal. But does that mean that it can't be used when the population distribution is normal? It can be used. But generally, when the population distribution is normal, we use z-test or t-test. It is called a non-parametric test, which means that it does not depend on the underlying distribution, whether it's normal or not normal. So when it's normal, we use z-test or t-test. When it's not normal, we use Wilcoxon and Whitney. But having said that, Wilcoxon or Whitney tests are generally used if the distribution is not normal. Third assumption is that the observations have to be ordinal, which means the observations which we are going to use as part of our experiment, that have to maintain some order. Fourthly, and most important, that Wilcoxon tests are done on the same group before and after an event. So, for example, I want to build a drug, and I want to apply the drug on a human being before, or rather, what I want is, I want to measure the impact of drug on the height of an individual. So I will measure take their measurements of few individuals before applying the drug and after applying the drug. However, that does not work with Wilcoxon. Wilcoxon is always on the same group. So generally, a same person undergoing multiple experiments, right? Like for example, let me give you an example. So here we are looking at the performance of students before joining a tutorial and after joining a tutorial. So we have recorded the marks of the students across 13 subjects. As I said, it has to be in the same group. A common mistake what I see is people apply this test on different groups. That cannot work with Wilcoxon. For that we have a different test. So here it's on the same group, but before and after a certain event. So here, who is the group? Group is my student 1. He is the focal point in this case. So we want to measure his metrics before and after an event. What is the event here? During the tutorial. So, and after joining the tutorial. So before joining the tutorial and after joining the tutorial, we have recorded the marks. Now what we want to find out? What we want to find out is, has there been any significant difference in the score of student 1 after joining the tutorial? Right? Can we observe any difference which we can call as statistically significant? So here are the scores before joining the tutorial and after joining the tutorial. So on a naked eye, what we can see is mostly the scores have increased. But is it statistically significant enough for me to say that yes, probably the tutorial is having an impact? So let's find out. So it's a very simple test actually. The calculation is not very complex. So first step, what we are going to do is, we are going to calculate the difference for each line item. In this case, these subjects. So here, for each line item, we calculate the difference. So as you can see, we have calculated the difference. before and after. So after minus before is what we have done. And we have seen that in these two cases, in these three cases rather, it's negative. Rest are all positive. So in these cases, we have seen that the marks of the student has increased. In these subjects, the marks of the students has decreased. So the next step, what we are going to do is we are going to calculate the absolute difference. So here, as you can see, we have a sign, but now we are getting rid of the sign. We are taking the absolute difference. So this is the absolute difference. So in the next step, so here, as you can see, this is the difference and this is the absolute difference. Now what we are going to do is we are going to create a rank. So as you can see, the lowest one is 0.1 as far as absolute difference is concerned. So we have given it a rank 1. Then 1 is a difference where we have given it a rank 2. 1.2 is rank 3. Difference of 2 is rank 4. 2.2 is rank 5. 3.1 is rank 6. 5.3 is rank 7, and so on. Now, in the next step, what we are going to do is we are going to identify where the difference was negative and we are going to add their rank. So as you can see here, we have added the rank where the difference was negative. And we also add the rank where the difference is positive. So from here, it's positive. As you can see that the sum is 75. And here, this is 75 and this is 16. 16 is the 3 negative ones. Now what we are going to do is we are going to take a minimum value of these two. So the minimum value, as you can see, it's 16. So we are going to take that and we are going to call it as W calculated. So here is my formula. So I have put W calculated as 16. Now, so let's remove this because let's keep that as a suspense. Let's also remove this. Okay. So now we are going to find the critical value. So let's look at a critical value from the Wilcoxon sign rank test. So here, what are my number of observations? It's 13. So am I doing a one-tailed or a two-tailed test? So let's start with a two-tailed test. So if it's a two-tailed test, then the critical value for alpha is equal to 0.5 is 17. So for alpha is equal to, so critical value is 17 for two-tailed test. So we just want to know whether there is a difference or not, right? So now we are going to follow this formula. What does this formula says? If W calculated is greater than W critical, in that case we cannot reject H0. Which means there is not enough evidence to reject, or there is not enough evidence against the null hypothesis. However, if W calculated is less than W critical or equal to, then we can reject H0 and accept H1. So in our case, this is true. So W calculated is 16. And W critical is 17. So we can reject H0 and accept H1. Now what is H0 and H1 here? H0, as you can see, it's a state of equilibrium. So which in this case is that median 1 is equal to median 2. What is H1? Median 1 is not equal to median 2. That means the performance of the student has changed after joining the tutorial. So here we are doing a two-tailed test to start with, right? So what we'll also do is that we will look at an online calculator and see how that behaves. for Wilcoxon. So this is a test. It's a two-tailed test. We are starting with a two-tailed test. And the significance level we have kept at 0.05. So we have kept the values before and after. And let's calculate. Let's see what do we find. So what we find is that the p-value is equal to 0.039, which means only 3.98% chances are there that the null hypothesis is true. So the chances of this incident to be true is 3.98%. That is less than 5%. So which means we can reject this hypothesis and we can accept this hypothesis. Now let's make some changes. So what we'll do is, say, let's make some changes to the score. Say I make it as, say, 14. Say this one is 12. I'm just trying to bring the scores closer, or say 12.5 rather. Say this is 18. So I have made some changes to the score. Does it make any difference in this case? So let's also make this as 8.5. Okay. So we have made some changes to the score. Let's do a couple more. Okay. So now we have made certain changes to the score. So let's see the impact of that. So I'll copy this entire thing from here and I'll paste it here. Now let's mark all the yellow ones where I have negative difference. Any other negative differences? Okay, I actually need to copy this as well. All right. So here is one more, and here is one more. So we have taken all the negative differences. Now we have converted them into absolute differences. Now let's try to do the ranking. So we have to be very careful here so that we do not make any mistake. So this is 1. This is 2. This is 3. This is 4. This will be 5. 6. This should be 7. 8. 9. 10. No. This should be 9. 10. 11. No, I'm again making mistakes. So let's do it. After 5.6. Oh, there's a 4.6 also here. See, this is very confusing. So 1 is this, 2 is this, this is 3, this is fine, 4, 5, 6 is fine, 7 is fine, this will not be 8, this will be 8, this will be 9, 10, 11, 12, 13. So now I think it's correct. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Fine. So here we have got the sum of positive negative differences as 19 and positive as 72. So let's do 19 and 72. Now we can see that we cannot reject H0. We have come into this zone now. We cannot reject H0. And if I want to know that what is the exact probability for null hypothesis, so what we can do is, let's try to copy this and try to paste it here. So this is before, and this is after. So now let's do the calculation and see what do we find. See, as you can see, H0 is accepted. Why? See the probability, 14.65%. Though I have hesitance to say that we'll accept H0 until the p-value is very high, I think the safer bet is to say that we do not have enough evidence to reject H0. So in this case, my H0 is 14.65, which means my chances that this statement is true is 14.65, which means there has not been any change in the performance of the student. Now, if I have to do a one-tail test on the same thing, say I'll say median 2 is greater than median 1, right? So if I have to do that, so what I'll do is I'll just make it a one-tail test. Let's say do before and after. It's obvious that it cannot be before, cannot be greater than. At least from this data set, we cannot say that before is greater than. Actually, I have given before greater than after, so it should be before less than after. Yeah, at least on a naked eye, we see that the after one is better. But is it good enough to say that it's statistically significant? Let's see. In that case, what is the p-value? Around 7%, around 7.32% chances that, right? Around 7.32% chances that we can not reject H0. And as you can see, the larger the p-value, the more it supports H0, because p-value always represents H0, which I have been telling throughout my lectures. Okay, so here the chances are that 7.3% chances are there that it has increased, or rather it has not increased, it has stayed the same even after joining the tutorial. Okay, so not only you should look into this table, at the same time you should also look at these online calculators just to find out what is the exact p-value, and that will make the subject even more interesting. Else just doing this calculation from here, putting in this formula, it's not a big deal. The fun starts when you start exploring and understanding what are the chances of the null hypothesis being true. So if you have followed my previous lectures, previous series, even this particular video, you have seen that I always stress on also finding the p-value. That makes it very, very interesting. Okay, so in this case, if median 2 is greater than median 1, the performance of the student has increased after joining the tutorial. That's the interpretation. But has it actually increased? Statistically, we cannot say that. We have to be at least 95% sure. In this case, we'll be probably 85.35% sure. So the chances of this statement occurring is 85.3535%. Right? Okay. So now what we will do is we'll look at another test. And this test is called the Whitney test. So here again, this is used if the distribution is not normal, the observations has to be ordinal. This is applicable to independent samples. This is called non-parametric because it does not depend on the underlying distribution. But what is the most important point is that the tests are done on two different groups. In Wilcoxon, we saw that the subject was one. I mean, subject, not the study subject, the experiment subject was student one, which was the same subject, right? Here, the experiment subject will be two different groups. So let's take an example of Whitney. Suppose here we have two movies. So movie A and movie B, and whatever you see on the these numbers, these are nothing but the ratings of the movie. So movie A has got certain ratings by the critics. Movie B has got certain ratings by the critics. Now, what we are going to do? We are going to create an ordered list. In the ordered list, what we are going to do? We are going to take the ratings from both the movies and put it here. And then we have ordered it. So first we took the ratings from both the movies and then we have ordered it. So here what is my objective? My objective is to find whether there is any significant difference between the ratings of these two movies or not. If we are doing a two-tailed test. For one-tailed test, we'll see again greater or lesser. But we want to prove things statistically. Is it statistically significant that movie A and movie B have got different ratings? They're different in nature, right? And here, as you can see, intentionally what I have done is I have made one less observation in movie 2, which means it's not mandatory that the number of observations has to be same. So this is done by purpose to show you that this test absolutely works even if the number of samples in the distributions are not equal. So here we have created the rank and we have ordered the list. So now what we are going to do is, as you can see, in a lot of cases, there has been a tie. I can see 1, 2. Actually, I think we need to order this. So what we'll do is, let's pick this one. Let's do it from scratch. Let's pick this one. Let's pick this one. So I will not consider this. It's fine. Put the borders. Now let's try to order this. Oh, I think it was correct only. So, oh yes, this was correct only. We had 3 2s. Sorry, my bad. Everything was correct. So here we have 3 2s. So all these 3 2s are coming at the top. So 1, 2, and 3. Then we have 2 3s, which are here. Then we have a 4. So this is the 4. We have 2 5s. We have 2, 6. And then we have 7, 8, and 9. So this is my ordered list. Now, what I have done is here, as you can see, these colors signify something. What we see is that all the 3 numbers are 2, but the rank is 1, 2, 3. Here again, both the numbers are 3, but the rank is 4 and 5, which is not correct, right? So I can tell you that what used to happen in my school days is that whenever we used to get same marks, since my name is Suvajit, it was like S was way behind in the alphabet, right? So any guys who are having names starting with A or B or C, right, D, in spite of having the same marks, my roll number was used to be behind. And when we used to study, the roll numbers, at least in my school, the roll number was based on the marks you get on the previous class. So a lot of times, in spite of scoring the same marks, just my name started with a different alphabet, an alphabet which comes later in the series. So my roll number was a bit behind in spite of getting the same marks. So here the same thing has happened. And this is not correct. This is not fair. So what we have done here is, as you can see, this is my initial rank, which is same as this. Then what we have done is we have created an updated rank. And how we have created this updated rank? So we have taken the average of these 3 ranks. So average of 1, 2 and 3 is 2, which we have put here. Average of 4 and 5 is 4.5, put here. Average of 7 and 8, here we are a tie here, so that is 7.5. Average of 9 and 10 is 9.5. So now we have made sure that there is no injustice. So we have created an updated rank. So now let's see what we can do with this updated rank. It's very simple. Now we go back to the original distribution and we plug these updated ranks. We plug these updated ranks against the movie ratings. Once that is done, we take a sum of these ranks. Sum of rank for movie A, sum of rank for movie B. Then we do something which we called as calculating mu statistic. So if you see, mu statistic is the rank sum minus n into n plus 1 divided by 2. What is n? The number of observations. So we'll do it for both the groups. So as you can see here, this is rank sum. Rank sum is B9 minus n, which is this count, into n plus 1 divided by 2. And here we have done the same thing, B9, which is the rank sum, minus n into n plus 1 by 2. And then we take the minimum of these 2 values, which is 5.5. So as you can see here, I have put this in the formula as well. So everything gets automatically calculated. So now let's come back to the calculation. So here we have got 5.5 as mu calculated. Now let's look at mu critical. So here is the Mann-Whitney table. So we'll get the critical values for here for our 2-tailed tests. So now what we'll do is, let's try to figure out this N1 and N2. And as you can see, there it can be different. So here in this case, my N1 is 7 because I have 7 observations. Here my N2 is 6 because I have 6 observations. So my N1 is 7 and n2 is 6, which means 7 and 6 intersects at these two rows. So the critical value at 0.5 confidence interval, or alpha, not the confidence interval directly, I'll check alpha at 0.05 is 6. So now let's take that and see. So the critical value is 6, and as you can see here, if mu calculated is less or equal to mu critical, then we can reject H0 and accept H1. And if mu calculated is greater than mu critical, then we cannot reject H0 because we do not have enough evidence to reject, or we do not have enough evidence against the null hypothesis. So as you can see here, the hypotheses are that rank 1 is equal to rank 2, which means the distribution is same, which means the movies are same basically, they come from the same distribution. And H1, the alternate hypothesis, is that the rank 1 is not equal to rank 2, which means the distribution are not same. So in this case, we have found that we can reject this theory and accept this theory. So if I want to know the exact p-value, which I always recommend you to do, because that makes the subject interesting. So here we have values from both the groups. We are looking at a two-tailed test at a significance level of 0.05. Everything is fine. Let's calculate. So what do we find? 3.05% chances of the null hypothesis being true. Okay? And as you can see, the smaller the p-value, the more it supports the H1, because p-value always belongs to H0, or my null hypothesis. Now, if I start to make some changes here, say for example, I make it 6. I'm just trying to make it closer to the original data. Now let's see what does it come. Now I expect it to be, I mean, we will not be able to reject the null hypothesis so easily. So here we have crossed the barrier, 5.86%. So the chances are that now we cannot reject the null hypothesis with at least 95% confidence. Let's try to bring them even more closer. Say, I'll do this, I'll try to increase this more. Let's try to see. Now what we see is something very interesting. The p-value has become very high, 94.16, which means 94.16% chances that the two movies are coming from the same distribution, right? Or maybe two movies are same, or the ratings are actually collected from the same distribution, or maybe if I just want to distinguish whether movie 1 and movie 2 are actually the same movie coming from the same distribution, you can think of various interpretations of that. But what we see is the p-value has become very, very high, right? So that's it on Mann-Whitney test. Now the last test for this lecture we will see for ANOVA. So the full form of ANOVA is analysis of variance. So now what we are going to do is, it's a different kind of test. So let's open Anova. So as you can see here, we have 3 movies and 4 critics, 3 columns and 2 rows. So far what we have seen is that we are comparing the same subject across 2 groups or maybe 2 different distributions. But with Anova, we see that there are 3 distributions, not 2. Moreover, Anova deals with variance. So far we have been mainly dealing with mean and median. So what does the basic premise of Anova? As we can see, there are 3 distributions. So whenever there is a distribution, they will have some variance. So movie 1 is going to have a bit of variance, movie 2 is going to have a bit of variance, movie 3 is going to have a bit of variance. So the point which we want to prove is the variance of movie 1, the variance of movie 2, the variance of movie 3, are they comparable or not? If the variances across the movie are more or less the same, right? Then in that case, what we can see is that probably the variance is not coming from this side of the data. The variance is probably coming from this side. Let's understand this intuitively. So here there can be 2 scenarios. One is that the critics are very different, which means they're for the same movie they're giving different kind of scores. Like this is movie 1, but suppose for example critic 1 gave 3, critic 2 gave 9, critic 3 gave 5, critic 4 gave 8. So what we see is that there's a huge discrepancy in the way that critics are giving the scores. Like for example, for this movie again, critic 1 gave say 4, critic 2 gave 8, critic 3 gave say 6 maybe, critic 4 gets 7.5. So as we can see, for the same movie, the scores by the critics are very different. Third scenario, say third movie, say critic gave 3.5, here critic gave 8, here he gave 7, he gave say 6.5. So here what we see is that the variance in the data is coming from the fact that the critics are very different. For the same movie, the scores are very, very different. However, when we look across the columns, we do not see much of a difference. So a particular critic have more or less given similar kind of ratings for 3 movies, which means the difference, the variation in the data, the total variation in the data can be attributed from this part, not from this part. So we call it as between or within. So this part is my within and this part is my between. So between the movies or within the critics. You have to think like that. Within is the row, the variance in the row, between is the variance within the column. So in this case, let's do the calculation. So we have to calculate 3 things. Sum of squares within, which is within the rows, sum of squares total, the total variance, and sum of squares between, that means between the columns. So how to calculate sum of squares within? So this is the sum of group mean minus each element square. So here, this is the group mean for movie 1, group mean for movie 2, group mean for movie 3. So now what I'm going to do, I'm going to take each individual observation and then subtract it from the group mean, square it up, and then keep on adding them. So as you can see here, for each group, for this group, we are taking this value, subtracting it from this, squaring it up, then adding, then we'll again do it for this, with this, with this, with this, with this. We'll keep on subtracting, squaring, and then adding all of them together. And that will give me sum of squares within, across the rows. Then sum of squares total is sum of grand mean minus each element square. What is grand mean? Grand mean is nothing but mean of all group means. So if I take all these three group means, I get a grand mean. Now from grand mean, I am going to take each observation, subtract it, square it, and then keep on adding it. So I'm going to have 12 additions. 12, subtract, square, and add. So as you can see here, we have 12 expressions. So that will give me sum of squares total. Now what is sum of squares between? Sum of squares total minus sum of squares within. And as you can see, sum of squares between is very, very low, which is expected because there is hardly any variance between them. But sum of squares within is very, very high. In fact, out of the total variance, it's all coming from within part, not the between part. So here, as we can see, between is very, very low. So now how to calculate ANOVA? So here we have to calculate something called an F statistics. So we have calculated SSB, sum of squares between. We have calculated SSW, sum of squares within. And as we can see, the formula is right here. So let me just squeeze it slightly so that you can see the formula while we do the calculation. I'll bring it here. Maybe here, yeah. So this should be fine. Right. So N is number of groups. How many groups are there? There is the number of columns is 3. N is number of elements within each group. How many rows? 4. M minus 1 and N minus 1, because as you can see in the formula, we need M minus 1 and N minus 1. So that is 2 and 3. Now we have to calculate the numerator and the denominator, and then we'll get the F statistic. So the numerator is 0.02. How is it calculated? Sum of squares between divided by M minus 1. So sum of squares between divided by M minus 1. Then F stat denominator, sum of squares within divided by M into N minus 1. So as you can see, M into N minus 1. So that gives me denominator. If statistic is numerator by denominator, which we get as 0.004. Very, very low. So now let's make some changes to the data and let's see how it behaves. So now let's try to create kind of a balance in the data. So let's try to create some difference between the movies. Here, so without doing any calculation, we can clearly say that there is no statistical difference, or there is the difference between the columns is absolutely not statistically significant. The value is very, very low, and the contribution is coming all from within, not from between. Now let's try to create some gaps within. So suppose movie 1 for critic 1, so he has given 5 here, maybe say 2.5 here, and say 8 here. Critic 2, say for the same movie, say 6, 7.5, or rather say 3, and say 7. Critic say 9, 6 is fine, or rather let me say this is 7, this is 4. So I'm just trying to create differences between the movies. So this is 7.5. And then last but not the least, so this is 6, this is 5.5, and this is say 9. Now we can see that the sum of squares between is high. Fair enough, but is it high enough for me to say that sum of squares between is there? So let's find it out. So this F stat which we have calculated is 16.27. So let's come here and plug it. So calculated is 16.27. Now we have to find the critical value. So we can find it from the F table. So degrees of freedom in the numerator and degrees of freedom in the denominator. So in the numerator, my degrees of freedom is 2, denominator is 3. So 2 and 3, which means this is 2, this is 3, and this is where I need to pinpoint. Now with 0.5 as the p-value, this is my critical value, 9.55. So let's just plug it in. So this is 9.55 at 95% confidence. Now let's see what is my H0 and H1. H0 is state of equilibrium. Mean 1 is equal to mean 2 is equal to mean 3, which means the variance between the groups is not more, but the groups are like very similar in nature. And the difference is coming from within the rows. And H1 is mean is not equal to mean 2 and not equal to mean 3, which means the variance of the between the groups is more, or the groups are not similar. And this can be ANOVA works when we have 3 or more groups to compare. It's not only 3, it can be even more. So now let's just plug the values. So this is 16.27, and the critical value is 9.55. We can reject H0 and accept H1. So what is my H0? This is my H0 which can be rejected. And this is my H1 which can be accepted. So variance between the groups is more. We accept this theory and reject this theory. Okay. So that is it from ANOVA. So we have learned a lot of tests, and with this we are going to complete the set of hypothesis test. Now we are in the next series we are going to look at correlation, covariance, and chi-square, which tests the relationship between categorical and continuous variables. If you have liked our videos, the prior videos, as well as if you like this current video, please like, share, subscribe, spread the word. We have tried to make it as intuitive as possible and as easy as possible. If you like it, please share the word. If you want to enroll for the course, you can just click on the link below, and then we'll be happy to have you in the course and discuss, learn, discover a lot of new topics. So statistics is the base for data science, and you have to get this right in order to make a career in data science. So thank you for watching this video, and I'll see you in another series. Till then, happy learning.